Welcome. So we'll learn this video on the topic of bending in composite sections. And composite members or materials or systems are very common in very different applications. So in skateboards, like you will see different designs, but you will find designs that have composite sections, and you will find some layers of plywood and like some carbon fiber embedded within. So you're dealing now with two different type of materials. Another example is concrete and structural concrete. Here we have a mix of two materials here. The concrete itself, or cement and gravel and sand, all of that. We assume it's homogeneous, so that's a big assumption, but this is a material, and then the steel reinforcement here is another material. So the section work together, concrete and steel, to provide the required rigidity or stiffness. And then another example is like SIPs, so structurally insulated panels. So there's a foam layer here that's kind of sandwiched by plywood, or wood. So these are different examples, very common examples of seeing different materials being used to build up members and sections. So we will see here how to deal with such cases. So sigma is equal to negative my over I, or sigma max is equal to mc over I. With this formula still applies here. The problem here is that sigma is derived based on strain, and if you're talking about, yes, the whole section here deforms together the same way, because we assume structure integrity here of the section. The wood and steel are very well attached to each other by glue, by nuts or nails. So they will deform together. Like if this is the beam, the beam will deform together even if it's made of different materials, wood and steel. So deformation and strain is the same, but we remember that the Young's modulus of both is different. So the stresses within will develop differently. So we will see here how to analyze the distribution of stresses and the stresses of different parts of this composite beam. But one thing we know, like I explained, kinematics and compatibility of stresses require that the deformation of wood and steel is the same at this exact point here. So what we'll use also is that the moment of inertia, the bending moment, is resisted by two properties. One is a material property, which is E, because it results in an axial normal stress, which is resisted by Young's modulus. It relates sigma and epsilon, the stress and strain. And the other property is I, the geometric property of the section. So the moment of inertia around the x-axis here, which is the same axis of the moment. So the idea is we will transform this cross-section that's made up of wood and steel in a way that allows us to analyze stresses of the same material, but maintain the same quality or resistance to the moment. So when I transform the section, it will have the same EI values still. So I will show that by like how to deal with this specific exercise here, or example, in this board. So the question is, like, how much of the moment is resisted by wood and steel? Because if we can figure this out, we'll figure out the stresses developing in the wood and steel. So to be able to answer that, we need the material properties. So the Young's modulus of this wood and steel are given. You can see here the steel is much stronger than wood because it has a higher E. So kind of I answered this already. Steel is stronger because Young's modulus is bigger. So if I say that if I have a 2x4 steel member, a cross section, I cannot replace it with a 2x4 wood. So I have to replace it with enough area that would give me the same strength. And strength here means resistance to deformation. So I will have the same deformation. That's the goal. So the question turns out to be how much of E steel is equal to how many E woods would be equivalent to E steel. So I can calculate this ratio, and it will be 15.38. And this ratio here, or this factor 15.38, I will call it the transformation factor. So I will use it to transform my section, this composite section, to different section, which is all wood section. So I will transform the steel from a wood in this case, and you can see here that the wood, the steel is transformed from 2x4 section. I'm keeping the depth 4 and I'm expanding the width to be 30.8, which is by multiplying by the factor of transformation here. And now if I apply these two beams or these two members to the same bending, they will deform at the same amount. They will feel the same strain. Stresses will be different because the area here is different, but the strain will be the same. So one thing here is I'm not transforming from steel to wood by expanding the height. Because remember, our goal is to have the same strain. You have to have the same resistance to bending, which is achieved by the same equivalent EI value. So if I'm moving from steel to wood, so I'm changing the EI value from a very strong E to a strong, a lesser or a weaker E from steel to wood. Then I have to reduce or increase the ratio of I. So I increase the value of I in the right section here of the wood, proportional to the drop in the E. So to have that proportional change, if you remember, I is equal to the width times the height to the power 3 over 12. To have that linear kind of proportional change, it's better to change the width, not the height, because the height is to the power 3. It will not be a linear change. Unlike E, I change it by a factor, so it's a linear change, 15.38. But to change, to keep the same EI equivalent between these two sections of steel and wood, I will have to change the width, not the height. And that will allow me to benefit from the compatibility of stresses and have the same flexure strains for both the original and transformed section. So if I go back to the steel and wood section, I will be able to transform it to either an all wood section. So I will keep the wood, the existing wood, and transform the steel to wood. And I will increase here the width by this factor of steel to wood, or transformation factor. Or I can do that, keep the steel and transform the wood to steel. So it will be an all steel section. You can see here this B prime now is reduced by the ratio of E wood over E steel, not the other way like we did in the all wood section. So which one to use? I mean, you might be confused. Is it E steel over E wood or E wood over E steel? Think about you're moving from what? A stronger material to a weaker material. So in the upper case here, I'm moving from steel to wood. I'm making all the section wood. So the steel that I removed, I have to replace it with much more material or area. So I'm multiplying by a ratio that should be more than 1. So I'm dividing a bigger E over a smaller E. And then you can think it the other way in the second case. So if I'm keeping the steel, I'm replacing the wood. Wood is weak, so I don't need really this whole area to be steel. I will reduce or shrink it, and that shrink means I'm multiplying by a factor of less than 1. So I'm dividing as the smaller e over the larger e. So that's conceptually here what are composite beams or composite bending members, members under bending. They're all over the place. We see them from skateboards all the way to building materials. And the idea is I'm trying to figure out how to analyze these sections under bending. And the first thing to do is figure out really what's I and how we can transform a section from a composite material to the same material that's equivalent still to the same type of behavior that I will see, and behavior here is the strain that will happen. So that's we learning how to transform the section. In the next video we'll see how to analyze now this transformed version of the composite section and figure out the stresses at different points. So we'll see that in the next video.